spiral wave patterns, like this, okay, right? And other types of wave patterns, because there are other types of wave patterns, okay, right? So, yeah. Yeah, okay. This one, couple of papers, okay? Basically, you need to solve a Navier-Stokes equation in a rotating frame. Yeah? Okay. I think it's better that from day one you know what you need to do, right? Rather than you know, yeah. Okay, so I'll just give you a very, sort of like just a preliminary derivation. I'm not going to solve the Navier-Stokes equation, okay, right? Just to highlight to you the terms that comes from the rotating frame. 1, 2, okay, right? So this is the centrifugal force, right? And this is the Coriolis force, okay, right? So there are again many papers in the market. So I'm not going to give you all the papers, right? So there are papers which discuss the relative importance of the Coriolis force, right, versus the centrifugal force. Okay, but I can just briefly tell you in one statement. Currently, both effects should be treated with respect, equal respect. Okay, right. So both of them will contribute some things. Okay, right. So I derive, that means plug in things and then. Right, assuming that the rotation is along the z-axis, right? And then I work out the Coriolis acceleration, centrifugal acceleration, and then plug it into this equation. This equation is very compact. It's actually made up of 3 coupled differential equations, coupled partial differential equations. Okay, right? You can scale it like in one of the papers, and then finally you get this set of equations. Okay. Now I need to warn you, I may make mistakes in these derivations, even though I don't think so, but but this paper, just to show you that those set of equations, I can't seem to be able to agree with this paper. I couldn't reproduce this term. Okay, right? This paper is Physical Review E, Volume 65, 026312. Okay, right? So if you can reproduce this term, please let me know. This is not the, I don't know whether is it the Reynolds number. I don't think so. Okay, right? So I don't know how he has this term, right? Even though my 2 other equations are exactly consistent with his. Okay, bear in mind, this equation, they are already going one step. They take that rotating platform, right, and they tilt it. Okay, this set of equations is actually for rotating platform tilted at an angle gamma. Okay, at an angle gamma. Okay, right. So, yep. For you, I think horizontal is enough, so, okay. Because this is a very old problem, I give you a paper from Reviews of Modern Physics that talks about thin films, dynamics, and stability. Okay, so you can see here, in particular, the films driven by body forces, right? Flows driven by gravity, flows driven by centrifugal forces. Okay. Right, this is the problem that we are looking at. Okay. Right now, when the papers arrive and you find one whole big stack, okay, take note of the order in which I put the papers. Okay, I put this actually as unfortunately I put it at the top. Not because it's the top paper that you have to read, right? But rather, this paper should give you a broad idea about the things that you should be concerned with when you look at this problem. Okay, this is very important, right? Those who have been to IYPT, right? You have to know, you have to know the problems. You have to know what are the problems that your opponents would have also, right? So that you can engage them properly, right? Okay? Right, so that is the Navier-Stokes equation in rotating frame. I hope this is the problem, the only equations that you need to solve the, this wave problem. Okay? Cat B. Cat B problems, because I know Cat B, you are younger, more junior, so I put more interesting problems for you all. Yeah? No partial differential equations. But if you like, you can have. The assurance optics. Knife edge. This is a knife edge. Dun, 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 dun. Okay, if you intend to do this before the November, when we have selection, for the selection, right? Set this up in the room and then show us. Yeah. You want to continue watching? Okay, right. I'm not going to show the second video. The second video shows you how to actually set up, one possible system that will display this. I don't show you because you can see here the video will take 21 minutes. So you can view this, in your own free time. Okay, right now. So right here. First thing is to set up first. Okay, right. So I'll give you a couple of papers. One of the paper is actually suggesting 3 possible ways that you can set up such a system using. You can find the materials around you, right? That allows you to make such a system. Okay, and right. Something I need to tell you. I will recommend this. This book is 400 pages, but it's good. Okay. So I'll give you I can only give you the table of contents. Okay, right, because of copyright thingy, you know, right? So you can see here that in the book, it even give you a historical background, right? And then this chapter I'll give you, okay, the basic concepts, right? I find it extremely useful, right? And then, of course, towards the end, it also gives you the mathematical models that you can use, okay, right, to model your optical systems, okay, right. So the book is quite useful. So this chapter will be given to you. A paper that summarizes, right, but I mean it's just basically really a summary, right, it's attached also. And then yeah, this is the paper that I said, will give you some details of how you can set up such a system. Okay? Right. And this problem is closely related to problem number 17. Yeah, if you have a nice system, right, like this, okay, problem number 17, you can use it.